The purpose of this segment is to introduce you to the concept of nucleophiles and electrophiles. By the end of this segment, you should be able to define the term nucleophile and electrophile, and you should be able to recognize examples of various nucleophiles and various electrophiles. So let's go ahead and get started with understanding the concept of nucleophiles and electrophiles. When we talk about nucleophiles and electrophiles, the reason that this concept is important is because much of our understanding of chemical reactions is going to be based on recognizing these so-called molecules that are referred to as nucleophiles and electrophiles. Much like they say with relationships between humans, opposites attract, the same is true in organic chemistry. We can think of nucleophiles and electrophiles as being opposites of one another, and they are going to be very attracted to one another, and they're typically going to react with one another. So the definition of a nucleophile, phile means love, nucleo is referring to nucleus. So a nucleophile loves the nucleus. A nucleophile, by definition, is going to be an electron-rich species. And electron-rich species, typically, since they have an excess of electrons, they're going to be very negatively polarized or have a negative formal charge, and that's going to make them very drawn to the positively charged nucleus. So hence, nucleophile. They are negative or negatively polarized, and they are very attracted to positively charged or positively polarized species. So nucleophile means nucleus loving, and we're going to see that nucleophiles, in order to have that excess of electrons that are available for reaction, nucleophiles must have either one or more pi bonds and or lone pairs. And it's going to be those lone pairs or pi bonds that are going to react as nucleophiles. They're going to be what does the work of a chemical reaction. So nucleophiles, to recognize those, typically what we're going to see is that those atoms are negatively polarized or have a negative formal charge. So they're typically going to be negatively polarized atoms or atoms with a negative formal charge. And typically the stronger nucleophiles, the more reactive nucleophiles, are going to be the ones that have that negative formal charge, because a negative formal charge is going to generally destabilize the nucleophile relative to just having a negative polarity. And when it's destabilized, that means it's going to be really eager to react as a nucleophile. So by virtue of having those pi bonds or lone pairs of electrons, the nucleophile has an excess of electron density, is the way that we could think of that. And that's going to make those very drawn to their opposite, their perfect match. Their perfect mate is going to be the so-called electrophile. So the electrophile, phile means love, electro is referring to electrons. Electrophiles love electrons because that is what they are lacking. They do not have electrons, and so they are very eager to mate with molecules or atoms that do have an excess of electron density. So electrophiles are typically going to be positively polarized atoms or atoms that have a positive formal charge. So we're looking for positively polarized atoms or a positive formal charge atom. So what we will see in chemical reactions is that our nucleophiles are going to be very drawn to electrophiles. Opposites attract, in other words. And when these have that natural, undeniable attraction for one another, what's going to happen is that it's going to be a very reactive attraction, and the nucleophile is typically going to form a bond to an electrophile whenever that is possible. So a couple of scenarios that we will run into that we're going to focus on here as we start our discussion of nucleophiles and electrophiles is what we refer to as a nucleophilic substitution reaction. So in a nucleophilic substitution reaction, what's going to happen is that one nucleophile is going to replace another, hence substitute. So we call this a nucleophilic substitution reaction. And the general reaction here, where we can pick out our nucleophile and our electrophile, is that we will have a carbon atom that is directly bonded to what we refer to as a leaving group, which I'm abbreviating as LV for leaving group, by saying LV or leaving group, that's implying that it's going to break away, hence leave. And the leaving group is typically an electronegative atom. And what's going to happen here when we have a carbon bonded to an electronegative atom is that that bond is going to be very polarized. And it's going to be polarized such that the carbon atom will have a strong positive polarization. In other words, that carbon will be electron deficient. And the leaving group would be negatively polarized because that's the electronegative atom. So common leaving groups, common electronegative atoms that you will see there are oftentimes halogens, because we recognize halogens as being some of the most electronegative atoms that we will see. So a very common leaving group, for example, is chlorine. So the part of this molecule that we're going to focus on here is the carbon atom, because that carbon atom is going to be very electrophilic. It's going to be very positively polarized because it has an electron deficiency, and that's going to make that carbon a good electrophile. And we said that electrophiles and nucleophiles are drawn to one another. So if we have in that reaction mixture a good nucleophile, which I'm just going to abbreviate as NU dot dot, that dot dot represents that the nucleophile typically has to have a pi bond or a lone pair. We're using a lone pair here. And that nucleophile we would expect, I'm just going to write nucleophile to make sure that we're clear on our definition. And that nucleophile has to have a pi bond or a lone pair, and it's going to be either a negatively charged or negatively polarized atom that we are dealing with there. So it has to have a negative formal charge or negative polarization. And what's going to happen in that reaction is that the nucleophile is very drawn to the electrophilic carbon atom. So it's going to want to form a bond to that electrophilic carbon atom. And when it forms a bond to that electrophilic carbon atom, so that that carbon doesn't go over the octet, because we're assuming here that this carbon is a tetrahedral carbon. I'll just put the total of 4 bonds to it. So if that nucleophile comes in and it wants to form a bond to that carbon, something has to leave. And what's going to leave is that halogen atom or other electronegative atom is going to break away, so that the nucleophile can come in and attack. So I'm showing that leaving group leaving by showing the covalent bond between carbon and the leaving group breaking and the electrons going on to the leaving group. So what happens here in this reaction is that by the end of the reaction, you will have a leaving group that then has picked up an extra lone pair of electrons because of the breakage of that covalent bond. And then additionally, that carbon atom that was our electrophile to start with is now going to have a new bond to the nucleophile. So it's as if the nucleophile essentially forced out the leaving group. So in other words, it's substituted in as the leaving group left. So that's what's happening here during this so-called nucleophilic substitution reaction. We're substituting a new nucleophile, Nu+, into the molecule as the leaving group leaves. And this is absolutely reliant upon having a starting material that is nucleophilic. That is something that has a negative formal charge or strong negative polarization. It has to have absolutely a pi bond or a lone pair available, and then it is going to come in and do what we would call attack, meaning it's going to use its lone pair of electrons to form a bond to the electrophilic carbon atom here. That has to be a positively polarized carbon atom. In order to be positively polarized, it needs to be bonded to the electronegative atom that's going to break away during the course of the reaction. So what that's going to leave us with is, as our product, our leaving group will have broken away and left, and our other product or organic product is typically what we're most interested in here, is going to have a new nucleophile bonded to it that is substituted in for the leaving group that has left. So what we can now ask, since so far we've been filling in this term nucleophile pretty generically, we can give some specific examples of atoms and groups that are able to act as nucleophiles. And certainly the list that I'm going to provide you of potential nucleophiles is not a comprehensive list. What you really need to be looking for when you're thinking about identifying nucleophiles is the concept of they have to have a pi bond or a lone pair of electrons available, and they're going to be negatively formal charged or negatively polarized. So I'm putting delta superscript negative there to indicate negative polarization. So some examples of nucleophiles that we will commonly come across include such things as we could have acting as a nucleophile methanol, which is CH3OH. In methanol, remember that we have a couple of sets of lone pairs on the oxygen atom that have to be there. That oxygen is going to be negatively polarized because it's the most electronegative atom in the molecule. And so that location of the molecule, that oxygen atom, could act as a nucleophile. So I've highlighted in yellow the nucleophilic atom out of there. We could also have acting as a nucleophile if, say, we had sodium NaSH. So in this molecule, remember, or in this compound, remember that there's an ionic bond between the sodium and the sulfur because the electronegativity difference is pretty big there. So the electrons are going to be exclusively held on the sulfur. So if we look at the structure of this, what we're going to have is like so. And so looking at this Lewis structure for this ionic compound, we can certainly recognize that the sulfur is what atom there is going to be able to act as a nucleophile because it is what has the pi bond or the lone pair. It's what has the negative formal charge or the negative polarization. We can also see situations where we can have as our nucleophile alkene groups, carbon-carbon double bonds, and I'm just going to plug in R groups here as the generic placeholders for what could be carbons or hydrogens to fill in this alkene. And in that case, it's going to be the pi bond that is able to act as the nucleophilic atom there. So that's what we could use as our electron donation source. Nucleophiles are going to be the electron donor. And as we go through, we can also look at just going through some additional examples of potential nucleophiles to come up with a broader list here. NaOH, remember that NaOH, much like NaSH, is Na plus, OH minus, and we have 3 sets of lone pairs there. And we'll go ahead and plug that in and highlight in yellow to indicate the nucleophilic atom. And it's no coincidence here that we're seeing that this is a base and also as a nucleophile. Nucleophiles and bases typically go hand in hand, because remember that a base by definition is going to be a proton acceptor. It by definition has to have some electrons in order to form a bond to the proton. Nucleophiles have to have a lone pair pi bond. So nucleophile and base pretty much go hand in hand here. So additional examples of nucleophiles that we can look at that may be a little bit more off the beaten path for you. NaCN. So if we take a look and dissect this out and plug in all of the electrons that have to be there to make a complete Lewis structure, we'd see that it's Na plus, and it's going to be a carbon-nitrogen triple bond. Have to have a lone pair on the nitrogen there, and to take care of all the electrons that are available, have to have a lone pair on the carbon. And as a result, that carbon is going to be a carbanion, a negatively charged carbon. And since it has actually both a lone pair of electrons and a pi bond there, that carbon is definitely going to be able to act as a nucleophile. We also see very commonly as a nucleophile a compound called sodium azide, which is NaN3. And if we go in and draw that out completely, again, we're going to see that the sodium is just a counter ion that's along for the right. It's not actually doing any work here. And then the azide group is an N3 group. And if we draw out and look at the different resonance structures of that, or what we have available here for that, what we're going to see is that the structure of sodium azide has a few different resonance forms that we can draw, but what's going to happen there is that we end up with this as the major resonance structure. And if we look at that major resonance structure of sodium azide, you will see that either of those 2 nitrogens on the end both have a negative formal charge, so either of those 2 could act as the nucleophile. And so what we're going to do in the next segment is we're going to look at reactions that involve these nucleophiles attacking electrophilic carbon atoms in the so-called nucleophilic substitution reaction. You should be very familiar with and able to recognize the nucleophile within a chemical reaction as the negatively charged or negatively polarized atom. Typically, it's going to be an atom that is relatively electronegative. And that's going to be what atom then attacks a so-called electrophilic atom, a positively polarized atom. So the sooner you get clear the definition of nucleophile versus electrophile and are able to recognize those, you're going to be off on the right foot for solving chemical reactions, because a huge number of different chemical reactions are going to rely upon our ability to recognize who's the nucleophile and who's the electrophile, because it's generally going to be the scenario that the nucleophile is going to be donating electrons from lone pairs or pi bonds to form a bond to an electrophilic atom. We're going to see that theme over and over and over again, and so what we're doing in the next few segments is introducing some types of reactions that rely on that, namely the so-called nucleophilic substitution reactions.